Hello, I am Professor A.D. Gunawardena. Today, we're diving into linear regression. So let's start. This awesome algorithm gives us insights into how we can predict things like the price of a product by analyzing different factors that influence it. By fitting a straight line through our data points, we can reveal patterns and make smart predictions. We'll walk you through the concept and show you some examples along the way. Ready? Let's get started. We will start with a data set on sales prediction. Our goal is to forecast monthly sales by examining key factors like advertising spend, promotions, and more. Picture this model as a linear formula connecting Y, our sales, with all the influencing X factors. The model is a simple linear model with error factor epsilon as part of it. We can even represent it in a sleek matrix form to capture all those relationships at once. The mission? To uncover the magic values of our beta parameters from the data. Once we nail those down, we'll have a powerful tool to predict future sales based on factors like advertising and promotions. Next, let's understand how linear regression is defined. So what exactly is linear regression? It's all about using data to make meaningful predictions. By mapping training data to continuous outcomes, regression can unlock insights like optimizing prices, forecasting sales, and so much more. We can start simple. Univariate linear regression focuses on one explanatory variable, x, to predict the outcome variable, y. But why stop there? Multiple linear regression ramps things up by using several explanatory variables to give us a clearer picture of y, the predictive variable how it compares to all the independent variables x. We'll explore plenty of these examples along the way. Get ready for some powerful predictions. When it comes to model estimation, we're looking at two main approaches, the general model and the univariate model. The general model is our go-to for data sets with a variety of sizes and features, helping us estimate the linear relationship between independent variables, x, and the dependent variable, y. On the flip side, the univariate model keeps it simple by focusing on just one x and one y. The goal for both? Minimize the mean square error, MSE. This means tackling an optimization challenge to find the beta vector that brings MSE as low as possible. By mastering these models and optimization techniques, we're set to create powerful, data-driven models that lead to smart decisions. Let's get optimizing. Now, let's break it down with a simple example. Imagine we have only one data point. We could come up with countless models that fit that single point, but let's be real, that's not exactly useful. Now, if we add a second data point, we can draw a line that passes through both, achieving zero error. Sounds better, right? But in the real world, we usually have a lot more data points, thousands, really. So, our task is to find the best line, the one that minimizes the mean square error, MSE. This way, we get the most accurate predictions possible, capturing the trend across all those points. All right, let's find the regression line with a fun example. But we use calculus here to minimize things. Imagine we have 3 points, 0, 0, 1, 0, and 2, 1. Our mission? To find the best fit line that minimizes the error for these points. We're assuming our model follows y prime equals sign mx plus b, and our task is to figure out the best values for m and b. We start by plugging each x value into the equation to get the estimated y prime for each point. With the actual and predicted values in hand, we calculate the square error for each point and then add them up to get the total square error loss. Now, to zero in on the optimal m and b, we take partial derivatives of the square error loss, set them to 0, and solve for m and b. Then, we plot this line along with the points. We'll see that it's the closest fit to all 3 points. And here's the best part. This method works for any number of points. Here is another problem we can solve, just like before, but with a twist. This time, our model is a quadratic equation, y equals sign ax squared plus bx plus c. This means we're fitting a curve instead of a straight line. To do this, we'll follow a similar process. Start by estimating values for each point using y equals sign ax squared plus bx plus c. Calculate the square error for each point based on these estimates. Add up all those errors to get the total square error loss. Now here's the trick. We need to find the values of a, b, and c that minimize this error. So just like before, we'll take partial derivatives of the square error loss with respect to a, b, and c, set them to 0, and solve for each parameter. Once we have our values for A, B, and C, plotting this quadratic curve alongside the data points will show us how close our model fits. If you want extra guidance or examples, check out the open-ended questions on qubits. Lots of tips and tricks are waiting for you there. As another example, let's dive into the model fxy equals sine x squared plus y squared, 2xy, and find its minimum value. To locate the minimum, we'll set the partial derivatives with respect to x and y to 0. Solving these equations, we find that x equals sine y minimizes the function. So any point along the line, x for any real number, xsx, gives us the minimum value. Here's the coolest part. When x equals sine y, the function's value is always 0. By exploring the gradients and partial derivatives, we can pinpoint the point that achieves the minimum error, right at the gradient sweet spot. This approach showcases how gradients guide us to the minimum point, giving us valuable insights into error reduction. So how good is our predictor? That's where the R-squared value comes in. The R-squared score tells us the proportion of variance in monthly sales, Y, that's explained by our features, X, in the data set. Suppose we created a model and find the estimated value Y hat and compare with the observed value Y. After crunching the numbers on the actual data set, give it a try on CodeBench if you're curious, we find that 96% of the variance in sales is explained by the selected features. Now that's a strong model. Next, we will look at ways to find the parameters of the actual model, including using gradient descent. Thanks for following along, and see you later.